Hello, welcome. What we're going to look at today is advanced mechanical principles, kinematics. We're looking at the crank slider system, which is part one of the assessment. If you didn't get the memo about the assessment, you may notice that we are missing the length of the con rod. I have asked you to use 500 millimeters for that, please. Right, so what is a crank slider system? Well, you'll normally see them drawn like this. Because the problem we have with the crank slider system in analysing it is that this is spinning. Because this is spinning, these angles are always changing and this position is always changing. So what we'll always have to do is analyse it at one position in space. If we analyse it at one position in space, then if we change that position at any point, the numbers should all fall through and everything should come out. Now, just to help us, what I've also done is I've found online on a site called GeoGebra, just about to show you it, is that when we look at GeoGebra, you should now be able to see the system. You can. Okay. If I change this angle and my crankshaft is going around with a rotational velocity, my slider is moving horizontally, and it's moving horizontally in the same reference as point A on this diagram. We will call that point O on ours. So we've got a system that we're going to model that's going to look something like that. Okay, so what we need to be looking at is how do we analyze this? Now, the first thing we need to do is work out what velocity this point here is moving at. And what we want is the tangential velocity of it. So what we mean by that is the linear velocity this is making perpendicular to the con rod. Okay, so what we need to do is start drawing our velocity diagram. To do that, though, we need a couple of values. So I'm going to take us back to my initial diagram. And just as a point of order, I am pretty certain that my connection is on the wrong screen, so just give me 2 seconds. I'm pretty certain that, there we go. This answer is incorrect. Now, woebetide freestudy.net, which is, you might recognize this question from pre-study, to be wrong, but I believe this should be 170 rads per second, and I'm going to prove why in a moment. Right, so first off, we need to know what the angular velocity of the crank is. So first off, we need to know what omega is equal to, and omega is equal to 2 pi times the speed in RPM divided by 60. So speed in RPM divided by 60 gives us the speed per second, times by 2 pi gives us how many radian there are per second. And that is equal to 2 pi times 3000 divided by 60, which is equal to 314.4. Please put a decimal point in. Rad per second. Once we know that, we can work out the tangential velocity of A with respect to O very easily, that the VA with respect to O is equal to omega times the radius of the circle. The radius of the circle is the length of our crankshaft. So the velocity of A with respect to O is equal to 314.4. Can't get decimal points. Give me a decimal point. 314.4 times 0.1, 31.44 meters per second. That is an important number. We will need that later on, and so we will underline that. In fact, we'll draw a red box around it. So we're going to need that number later on. Similarly, to help us do our diagram, although it's not specified, we will also need to know what this angle, and I'm going to call it angle alpha. Okay, we also need to know what angle that is to help us draw our diagram. So I'm just going to come across here and using the sine rule, sine of alpha over 100 is equal to the sine of 60 over 200. So alpha is equal to the inverse sine of 100 sine 60 over 200. Alpha is 25.66 degrees. And again, I'm going to need that in a minute. So I'm going to draw a red box around that as well. Okay, we now have all the information we need to determine the velocity of the crank, of the slider, and the angular velocity of the conrod at the point given. Clearly, that slide, if I go back to GeoGebra just briefly, here we go, share files, share files. If I just quickly go back to GeoGebra, then you'll see that if I take this angle, I run it through, that slider, its velocity stops at that point, it accelerates through to its fastest speed in the middle and then stops at that point and then comes back. So its velocity is not constant throughout. Okay, but it will start and stop. So I'll go back and come back. Right, okay, just wanted to do that. Right. So coming back, we're going to now look at the whiteboard. So to get the velocity, the easiest way is to draw a triangle, because everything is always with triangles. So first off, we need a line to represent a plane between O and B, which is the horizontal plane between the crank and the slider. So I am just going to come in here, do my best. Oh, started too far away. Come in here, do my best with a rule. And let's do this. Get my line. I'm going too far that way. There we go. Get myself a reference line. Right. My crank is set at 60 degrees and my velocity, my tangential velocity, is 90 degrees to that. So with this principle then, what I'm going to be doing is drawing a line, straight line, trying to find my line, trying to get my line lined up. Right, okay, there we go. Straight line down. Okay. Pardon that. Excuse me a second. Get to that. Come here. Delete you. Come here. No, not you. Come here. Yeah, I can't delete that. Apologies. Right. So this line here. Let's do that again. Okay. So what we're doing is our line this really isn't working well. Our line comes down from our angle. Now the angle that line makes to the horizontal for us is 30 degrees, because 90 minus 60, which is the angle our crankshaft is at, is equal to 30. Okay, the length of this is a scale, and I did 1 centimeter equals 2 meters per second. Okay, so that means that this line is 15.52 centimeters long, or as best as we can get it. Okay, this is our velocity vector of A from O. Okay, with me so far. Right, now that angle we developed, 25.66 degrees, is the angle the conrod is making with the horizontal. Okay, we're going 90 degrees from that, so we now want an angle up from the horizontal here, or an angle down from the horizontal here. It doesn't matter which. I tend to prefer to go up from this point. Okay, of 90 minus 25.6. Which is oh, come on, help me out. 64.34 degrees, as best as we can. Okay, so that line now wants to come up from here and all we're going to do is draw a line, make sure it passes through there. So yours is going to be drawn. Right, okay, I've drawn that slightly off. Fortunately, with my super technology, I can move it slightly so it wants to be there. And in essence, just dot a horizontal. No, sorry, I'm still. Just dot a horizontal in there. That angle is 64.32 degrees. So what that means is that, I'm not going to put this in red, if I can find my mouse, in red, coming along the top here. In fact, let's put in a line. coming in the top here in red, that line, okay, this is point B. Oh, sorry, then black. This is point B here, and the length of this line should be 17 centimeters, which is equal to 34 meters per second if everything's drawn correctly to scale. Now, because of this linearity, because this is all to scale now, the velocity of B with respect to A can also be worked out if we want, but we don't need that in the question. Okay, we're measuring the length of that line. Okay, so the answer to part 1 is 34.1 meters per second. It's gotten by drawing this velocity diagram. To get the second part, to get the angular velocity of the A, okay, what we have is we have the tangential velocity. We have V of B with respect to O, which is equal to 34 meters per second. If that's the tangential velocity, then omega is equal to VBO divided by the radius of the spin, which is equal to 34 divided by 0.2 meters, which is 170, near enough, rads per second. Thank you. That's how we do that first part. I hope that has been helpful for you, and I hope to come again and do a slightly more fluid one, but I'm learning this software as quickly as you are, so thank you very much.